Hello everyone, I'm Malka Jangir from IIT Kanpur. I'm your TA for Basics of Materials Engineering. Today's topic is Mechanical Properties of Materials, and this course is offered by Professor Ratna Kumar from Department of Mechanical Engineering from IIT Madras. So firstly we'll be going through some assignment question examples. So these will help you in solving your assignment questions, and then we'll be going through some notes of the lecture. So your first question is, in a standard tensile test near the elastic limit zone, then you have to complete the sentence. So your options are: tensile stress increases in linear proportion to the stress, or tensile stress increases at a faster rate, or tensile stress decreases at a faster rate, or none of the mentioned. So your answer will be C. Tensile stress decreases at a faster rate. And this can be explained using this stress strain curve. So in this area near elastic limit, after this area, this strain hardening part comes. So here your strain increases faster compared to your stress. So as it states here, tensile stress decreases at a faster rate. So it is due to strain hardening. So here your dislocation density increases, which leads to increase in the stress required for deforming the material further. Second question is, during tensile testing of a specimen using a universal tensile machine, the parameters actually measured include: options are true stress, true strain, or Poisson's ratio and Young's modulus, or engineering stress and engineering strain, or load and elongation. So your answer will be load and elongation. So when we perform test on UTM, so what we give, the input will be your extension rate. So your extension is measured compared to load. So load is measured using load cell. So your load and elongation is measured, and based on your initial cross section area of the sample and gauge length, you measure your engineering stress, engineering strain, and using the constant volume principle in plastic region, you can use formula for true stress and true strain for calculating these factors as well. Third question is, which statement is correct? And your options are: necking starts at the yield point, or yield point phenomena are seen in aluminium, and third is endurance limit can be determined by tensile testing, or yield strength is structure sensitive property. So one of the statement is correct and last statement is correct here, and other statements are incorrect. So in case of this statement, yield strength of material changes with microstructure. For example, annealed, normalized and hardened steel of the same composition will show different yield strengths. And for the first statement, necking starts at the ultimate tensile strength point. So it is the maximum load in the curve will be where your necking starts. And second statement is, yield point phenomena are seen in alloys with small amounts of interstitial atoms such as mild steel. And in case of aluminium and copper, these ductile materials, you won't be seeing yield point phenomena, but so that's why you require 0.2% offset to measure yield strength. Third option is, endurance limit can be determined by tensile testing. So it is wrong, because endurance limit can be determined by fatigue testing, while tensile testing gives tensile properties such as elastic modulus, stress strain, and yield strength, etc. Fourth question is, what is the ratio of Young's modulus of elasticity to the modulus of rigidity? Modulus of rigidity is G, shear modulus, in terms of Poisson's ratio. So your options are 2 times 1 plus mu and 1 plus mu, 2 times 1 minus mu and 1 minus mu. Answer will be first one. So this is the relation that's given for shear modulus and Young's modulus. So Young's modulus equals to 2 times shear modulus times 1 plus mu. Mu is your Poisson's ratio. E is elastic modulus, G is shear modulus. So when you keep E upon G, it will be 2 times 1 plus mu. Fifth question is, Rockwell test utilizes blank a measure of hardness. Your options are load, depth of indentation, diameter of indentation, and time of loading. So load and time of loading is fixed according to whichever scale you take, and depth of indentation is the measure of hardness. So this is the formula that is used in Rockwell hardness number. So it is N minus HT. So here your H and N, these are scale factors. So these depend on whichever scale we choose. For example, A, B, C, D. These are some scales in Rockwell hardness. So depending on that, these scale factors are decided. And D is your depth of penetration in mm. So depending on that, your Rockwell hardness is calculated. Here the H value is 500 for scales of B and C, and N can be 130 and 100 for different scales B and C respectively. Now question 6, you have to identify all correct statements. So your options are, resilience is computed as the area under the stress strain curve. Resilience is computed as the area under the stress strain curve in the elastic region. Toughness is computed as the area under the stress strain curve until fracture. These both statements are correct. And this statement, the relation between the true stress, engineering stress, true strain and engineering strain is given by sigma T equals to sigma times 1 plus E. This is also correct. And ET, which is your true stress, equals to ln 1 plus E. This is also correct. These are valid only up until the onset of necking. And fourth option is, the deformation of a ductile material is homogeneous until fracture. This statement is incorrect. So this statement is your after necking starts, there will be a drastic decrease in cross section in a localized region. So it's not homogeneous, it is non-uniform deformation after UTS point. Seventh question is, identify all the correct statements. So your options are, during elastic deformation, stress is proportional to strain, and the modulus of elasticity is a measure of stiffness of the material, and the modulus of elasticity is not significantly affected by heat treatment or alloying. And an external force acting on a polymer material produces an instantaneous elastic strain which remains constant as long as the stress is constant. Your answers will be the 2 and 3 statements. Other statements are incorrect. So in first statement, during elastic deformation, stress is proportional to strain. So this is not necessarily correct for all materials. So in some materials, during elastic deformation, stress is not proportional to strain. So there can be non-linear parts as well in the elastic region. For example, in grey cast iron, polymers, concrete, etc. Eighth question is vibration damping in machinery. Lathe is best achieved by means of base structure made of. So your options are low carbon steel, ductile cast iron, grey cast iron, white cast iron. Answer will be grey cast iron. So this can be explained by saying that in case of lathe beds, they are made using grey cast iron because of their high damping capacity and noise reduction, and its ability to create complex structures and cheap cost are the driving forces behind its popularity. And damping is one of the main factors to take into account because vibrations that occur while using a lathe are brought on by noise, mechanical movements and altering currents, and the damping capacity, which is higher in grey cast iron, it dissipates energy which lowers the vibrations and noise. Ninth question is ratio of elastic modulus and shear modulus is 3. Then what is Poisson's ratio? Your options are 0.33, 0.25, 0.50 or 0.40. Your answer will be 0.50. So as I told earlier, this formula is used. This is the relation between elastic Young's modulus and shear modulus. So elastic modulus equals to 2 times G and in brackets 1 plus mu. And here mu equals to E upon 2G minus 1. So here E upon G is given as 3. So 3 by 2 will be 1.5 minus 1. So it will be 0.5. The hardness of a material is the resistance of a material against. Your options are oxidation, indentation, twinning and fatigue. Your answer will be indentation. So hardness is defined as the resistance of the surface of material against plastic deformation through indentation or scratch, and oxidation resistance is chemical property, and fatigue resistance is also different from the hardness. Now properties of materials. So now we'll be going through some lecture notes. Okay, so firstly, the properties of materials. So these can be of various types. These can be mechanical, these can be physical or chemical properties. In case of mechanical properties, whatever mechanical force is applied, so in response to that, what your properties will be, they'll be mechanical properties. So examples are strength, toughness, hardness, ductility, elasticity, fatigue and creep. For physical properties, these are dependent on the physical state of the matter. So this can be density, specific heat, melting, boiling point, thermal expansion and conductivity, electrical and magnetic properties. Third is chemical properties. So it can be oxidation, corrosion, flammability, toxicity, etc. So it depends on your chemical composition of material. Now we'll be talking about mechanical properties. So in case of mechanical properties, they are useful for estimating how parts will behave when subjected to mechanical loads such as forces, moments, etc. And in particular, we are interested to know when the part will fail. For example, it breaks or otherwise changes shape, size, to go out of specification under different conditions. These include loading under tension, compression, torsion, bending, repeated cyclic loading, constant loading over a long time, impact, etc. Now we are interested in their hardness and how these properties change with temperature. These are some mechanical properties. So for finding out mechanical properties, we perform a uniaxial tensile testing test. So in this, we get a load versus extension graph, which can be converted into stress versus strain graph. Now this graph, in this linear part, it is your elastic deformation. So in this part, only interatomic bonding length changes, and when we remove this load, then your material takes its original shape, original size, dimensions. And if we go beyond yield strength, yield point, then we see it is the plastic part. Now here it is plastic deformation and up to maximum stress. After that it shows necking. So, and up to this it is uniform plastic deformation. And this part, your cross section will be uniform in all area gauge section. And after necking there will be a localized deformation, and in that area only gives most of the part of this curve afterwards, which is non-uniform plastic deformation, and then there will be fracture. Maximum is known as ultimate tensile strength, and the fracture stress is known as fracture strength. Now these are the properties that can be that are mechanical properties and are measured extensively, which is tensile strength, ductility, brittleness, resilience, toughness, impact strength. So this impact strength and brittleness are the only ones that can't be calculated using this graph, and others can be calculated using this. Now why we need to determine the mechanical properties? So this can be done by, as I told earlier, uniaxial tensile testing. Then we'll be getting the data and getting, after analysis, we'll be getting properties. Now based on these properties, we design our materials, their dimensions and their thickness and different sizes. These all are decided using these properties, so that we can make this design economic and we can reduce the consumption of material. Now two important parameters in mechanical properties is stress and strain. So in this stress, the internal resistance force per unit area acting on a material is called stress. It uses the original cross-section area of the specimen and is also known as engineering stress or conventional stress. Sigma is equals to F upon A naught, and your unit is Pascal or Newton per meter square. Now in this case, we see that as the length is, initial length is this in blue one. So after this we are applying uniaxial type of tensile loading. So we are pulling this in this direction, and then it's reducing its cross section and increasing its length. So final length is L, initial length is L naught, and initial cross section area is A naught. So sigma can be given as F upon A naught. Strain is defined as the change in length per unit original length. So it is unitless and also known as engineering strain or conventional strain or normal strain. And its formula can be given as delta L upon L naught. Sometimes strain is also expressed in microstrain, where multiplication factor will be 10 to the power minus 6. So here delta L is your change in length. Now Hooke's law is important in your elastic region, and within the elastic limit, low strain values. In this area, the stress is directly proportional to strain, and the behavior of solid is linear elastic, and the constant of proportion is called elastic modulus. Now sigma equals to proportional to epsilon, and there will be a constant proportionality constant capital E, which is known as elastic modulus. It also holds good for stresses and strain in simple compression, and in the same way for shear stress as well. Shear stress is symbol will be tau, and it is proportional to shear strain, which is gamma, as tau equal to G times gamma, where G is the shear modulus. Now the pressure is proportional to negative of the dilation volumetric strain, because positive pressure causes a shrinkage of volume. Hence P equals to minus K times the delta V upon V, where K is the bulk modulus, and all three moduli have the same dimension as that of stress. Now from this stress strain curve, we can see that initially in this elastic region, the slope of this curve will be your elastic modulus. For the elastic deformation in which stress and strain are proportional. So in this plot, the stress versus strain results in a linear relationship, and the slope of this linear segment corresponds to modulus of elasticity. This modulus also refers to stiffness or resistance to elastic deformation. This elastic deformation is non-permanent, so as we remove this load here, then it will follow the similar path that it followed during loading, and it will show zero strain in material. It will regain its original size. In case of elastic deformation, even small changes in interatomic spacing and stretching of interatomic bonds takes place, and the magnitude of elastic modulus is a measure of resistance to separation of the adjacent atoms. So these interatomic bond, it changes, so because at the equilibrium it has the lowest potential energy, and it is having least energy of the system. So as it deviates from the equilibrium, it will lead to some energy storage. Now modulus of elasticity is slightly affected by allowing heat treatment or cold work, as it really depends on the nature of atomic bonding in the material. So this type of this curve, potential energy versus distance, this interatomic distance, it also decides your elastic modulus. In case of elastic deformation, few materials exhibit non-linear elastic response, such as grey cast irons, polymers, concrete, and determination of modulus of elasticity is not straightforward, and the tangent or secant modulus is used as a measure of elastic modulus. So for example, if we require for this particular type of curve in elastic region, we want to measure its modulus, then in case of tangent, we'll be drawing a tangent, and slope of this tangent will be your tangent type of elastic modulus. And if we want second type of, then we'll be from that point we'll be joining it to the zero, and slope of this line will be your second elastic modulus. Now elastic limit is the greatest stress that a material can withstand without any measurable permanent strain after unloading, and yield strength is stress at which a material begins to deform plastically. Now when we measure the stress strain curve, then separating these two is relatively hard, and it is difficult to separate these. And so for yield strength, sometimes we also use 0.2% offset type of method. So it is determined by stress corresponding to the intersection of the stress strain curve and a line parallel to the elastic line offset by a strain of 0.2%, which will be 0.002 of your strain. So we'll be drawing, in this case we have a upper yield point, so in this case we won't be using it, but in case of when we use aluminium type of sample, so for example in this case we'll be plotting a parallel line from 0.002 strain, then where it will be cutting we consider it as a deviation from linearity and we take this as yield strength. And tensile strength or ultimate strength, it is the maximum load here divided by original cross section area A0 of the specimen, and the elongation is final length minus initial length divided by initial length, and for percent we can multiply with 100, and this is also called your ductility. Now percent reduction in area, it is initial area minus final area divided by initial area. For plastic deformation, for many metals, elastic deformation is up to a strain of 0.005 and material enters plastic regime if deformed beyond, and Hooke's law is not valid anymore. So breaking of bonds with original atom neighbors and reforming bonds with new neighbors takes place, and upon removal of stress the atoms or molecules, they do not return to their original positions, so there will be some permanent deformation. In case of crystalline materials it occurs by slip, and in case of amorphous materials it occurs by viscous flow. For some metals, elastic plastic transition is very well defined and plastic deformation starts at the upper yield point. Drop in the engineering stress and oscillation about a constant stress called lower yield point, and the further increase in stress with increase in strain. So pinning to obstacle at solute atom leads to upper yield point, and the breaking of pinning leads to drop in stress. So it can be seen here. So we'll be getting this upper yield point, then there'll be dropping. So because of pinning and unpinning of dislocation, and this area is because of formation of Cottrell atmosphere in case of mild steels. So in this case we can easily get upper yield point and lower yield point. We face problem in these type of curves, which will be for aluminium and copper and other pure ductile metals. So for these we take 0.2% offset for getting yield strength. And this is how your specimen dimensions will be changing with the curve. So this curve is corresponding to aluminium one. So in this case, in linear part it will be regaining its shape. So there will be very less of the strain seen in this part. Higher strain will be seen in this plastic part. So your entire cross section will be similar, uniform, and up to here we'll be seeing a necking in this area. Necking will be your reduction in cross section area. So after this your deformation will be restricted in only this necking area, and this material will fail from this necking area, and this will be your fracture strength, and this is your ultimate tensile strength. In case of polymers, they show various types of plots. So they can show ductility, very high ductility like this type of graphs as well, and some with very brittle materials as well. So this is one of the graphs for the thermoplastic polymers. In this case, initially it will be showing your elastic part. then it will be showing a maxima, then it will reduce because of formation of neck. Now here necking corresponds to your yield point in polymers. Now it will reduce because of this formation of neck, and less load is required for elongating this neck. Then in this area, this entire length will start to get uniform in the gauge section, that will correspond to CD. And after that again strain hardening will occur. When it will become uniform, then orientation hardening will take place in this area, and it will lead to finally fracture. Now various types of mechanical test are, first is tensile test. In this will be applying pulling type of loading, and the cross section will be reducing, gauge section will be increasing. And in compression, your cross section will increase, length will decrease. In shear test, you'll be applying just change in shape will takes place according to theta. And in case of torsion, your one face is fixed and you'll be applying a torque type of so there'll be an angular type of force that will be applied. Now this is the tension test. So here this is a screw driven type of UTM machine. So here your moving head is moving at a particular extension rate, and then this load is measured using load cell. Then this is your extensometer. So extensometer is used in case of when we want to measure elastic modulus more accurately for metallic samples. So this will give you a more accurate elastic modulus. Now this is your specimen that we'll be using. It is a dog bone shaped type of sample. So we use this type of samples because the cross section is lower in this area. So when you'll be gripping your sample in your machine, so there'll be stress concentration at this part. So we don't want the sample to fracture from this part where we are not measuring the stress strain, and we don't want material to fail from this part. So we want to measure in this part, so we are keeping its cross section less so that stress is higher and this area reaches to the fracture strength earlier compared to this one. Now true stress and strain. True stress strain curve gives a true indication of deformation characteristics because it is based on the instantaneous dimension of the specimen. And in engineering stress strain curve, stress drops down after necking since it is based on the original area. In true stress strain curve, the stress however increases after necking since the cross-sectional area of the specimen decreases rapidly after necking. The flow curve of many metals in the region of uniform plastic deformation can be expressed by the simple power law. So your sigma will be equals to K times epsilon times the N. So K is your strength coefficient, N is your strain hardening exponent, N equals to 0, which is for perfectly plastic solids, and N equal to 1 for elastic solids. And for most metals it is between 0.1 to 0.5. Now this curve, true curve, will always be higher compared to your engineering stress strain curve because we are dividing with the initial cross section, which is larger compared to instantaneous one. Now for true stress, true strain, we can use some formula for calculating because we are not instantaneously measuring cross section area and length. In case of engineering stress, it's load divided by original cross section, and for length it is change in length divided by original length, or in terms of area because of constancy of volume. In case of true stress, true strain, we can say by P load divided by instantaneous area. Now we multiply A naught with both of these, then this part becomes your engineering stress, and A naught upon A can be written in terms of length, and we can say this 1 plus E. And in case of your true strain, it can be written as dl upon L integration from L naught times L. So ln L upon L naught can be finally written as ln 1 plus E. For Poisson's ratio, due to elongation along z direction, there will be contraction in x and y direction. So if the material is isotropic, then the concentration contraction in x and y direction will be same. And theoretically, Poisson's ratio range for isotropic material is between 0.25 to 0.5, and for metals it's between 0.25 to 0.35. In case of auxetic materials, the lateral expansion due to longitudinal expansion occurs and they show negative Poisson's ratio. Now this is how your material, if we are pulling it in this direction, and initial is with dashed line, so lateral strain will be in this direction, and Poisson's ratio can be written as lateral strain divided by longitudinal strain. Now ductility and brittleness. So for ductility, we measure the degree of plastic deformation that has sustained at the fracture, and the strain at fracture is the percent elongation is greater than 5%, or strain is 0.05%. more than this, then it will be a ductile material and it will be having a well-defined yield point. In case of brittle material, a material that experiences very little or no plastic deformation upon fracture, it will be a brittle material. In this case, your strain will be lesser than 0.05 or less than 5%, and it does not exhibit an identifiable yield point. Now this is how your brittle fracture looks like, and it is comparatively, there will be less neck, there won't be any necking. In case of ductile fracture, there will be necking, and after necking there will be void nucleation because of some inclusions, and these voids will collapse and will lead to formation of crack. Then this crack will propagate and lead to fracture. This is cup and cone type of fracture will be in this case. Now resilience is the capacity of a material to absorb energy when it is deformed elastically, and then it recovers some same upon unloading. Now this area under this curve up to elastic limit, it will be your resilience. Now modulus of resilience, which is strain energy per unit volume required to stress a material from an unloaded state up to the point of yielding. SI units is joule per meter cube. So your it can be either we can integrate this curve up to this point, or we can get it using formula. It is in shape of triangle, so we can just multiply sigma y times EY times half, or we can get it in terms of elastic modulus as well. So it will be sigma y square upon 2a. Now resilient materials have high yield strength and low modulus of elasticity. For example, beryllium, copper, and this property is used in spring applications. toughness, it is measure of ability of material to absorb energy up to the fracture. So whole area is integrated under this stress strain curve up to fracture. It is represented by total area under stress strain curve up to fracture point, and brittle material has comparatively high yield and tensile strength but low toughness due to lack of ductility. So brittle material have less area. Ductile material are tougher than brittle ones. So this is not necessarily true as well. So in case of some polymers, they can have lower toughness than brittle ones as well. For example, it is shown here. In this case, this material has very high ductility but has very small toughness, which are unreinforced polymers. In case of metals, they have very large toughness because they have high UTS as well as high ductility. In case of ceramics, they have very high UTS but they have low ductility, so they show small toughness. Impact testing. Now materials when tested in under tensile testing, the strain rates given are very low compared to what we give in impact testing. So in these tests, the load swings from a given height to strike the specimen and the energy dissipated in the fracture is measured. The metallic samples, they tend to be square in cross section, while polymeric test specimens are often rectangular. The factor affecting impact energy. So for a given material, the impact energy will be seen to decrease if the yield strength is increased, and the notch serves as a stress concentration zone, and some materials are often sensitive towards notches than the others. Now the most of impact energy is absorbed by means of plastic deformation during the yielding. Therefore, factors that affect the yield behavior, hence ductility of the material, such as temperature and strain rate, will affect the impact energy. So for example, your temperature, if we reduce temperature, then impact strength generally reduces, and if we increase strain rate, then your impact strength reduces. In case of ceramics, they have very low impact strength compared to metals, polymers and composites. Metals show highest impact strength. Other property is hardness. It is a measure of material's resistance to localized plastic deformation. For example, a small indentation or a scratch. The advantages of hardness testing. So it is simple and inexpensive technique, and no special specimen preparation is needed, which is needed in case of, for example, scanning microscope, microscope and scanning electron microscope and TEM and other methods, or we are doing for example tensile testing, then we need to prepare the sample according to dimensions, and in case of impact testing as well, while here we don't require any specimen preparation, and the apparatus is also relatively cheaper. It is non-destructive method, so the small indentation is made so it won't destruct your sample. Other mechanical properties like tensile strength and fatigue strength can be obtained from the hardness data. Now, three types of hardness measurements are there. First is scratch hardness, and indentation hardness, and rebound or dynamic hardness. Scratch hardness is used for mineralogists, indentation hardness is used for engineers, and rebound and dynamic hardness is used when we don't want to destroy our sample, and it is a non-destructive type of test. Now, quantitative hardness test. So in case of Mohs scale, it is used on the ability of one material to scratch another, and the hardness is measured on a scale from 1 to 10. 1 will be your softest material, and 10 will be hardest. So here your Mohs scale is given. So these are various minerals, and Mohs hardness for 1 it is talc, 2 is given for gypsum, 3 is given for calcite, 4 is for fluorite, 5 is for apatite, 6 is for feldspar, 7 is for quartz, 8 is for topaz, 9 is for corundum, 10 is for diamond. Now, for example, if we got some metal or some mineral, then we can use these minerals to scratch them. So if I'm scratching it with apatite and this apatite is getting scratched, then I know that its hardness is higher than 5. And if feldspar is able to scratch that, then it is between 5 and 6. And macro hardness test are where the indentation will be bigger in size. So your Rockwell hardness test, Brinell hardness test, and Vickers hardness test. These are macro hardness test. Micro hardness test, here your loads will be smaller and your indentation size will be smaller as well. Now first is Knoop micro hardness test and second is Vickers micro hardness test. In this Vickers hardness test, your load will be in kgs, while here it will be in grams. First test is Brinell hardness test, which was proposed by J.A. Brinell. In this indent, we indent the metal surface with a 10 mm diameter steel ball at a load of 3000 kg. It is for hard metals and 500 kg is used for soft metals. For very hard metals, we use tungsten carbide ball and instead of hardened steel ball. Now the load is applied for a standard time, usually 30 seconds, and then load is removed, and then we measure the diameter of the indentation. Now the Brinell hardness number is given by this BHN, which is having formula load upon this pi dt. Now this can be in form of diameter as well. T will be your depth. T is your depth of indentation in mm, and capital D is your diameter of the indenter, and small d is your diameter of indentation. Now for using non-standard indenter size, one should make sure that the BHN does not change and their geometry is kept constant by using this relation. So P1 upon D1 square should be equal to P2 upon D2 square. Now the ultimate tensile strength in MPa can be given as 3.4 times the BHN hardness for heat treated plain carbon and medium alloy steels. Now along with BHN, the condition should also be mentioned. So you should also mention what load you took and what was your indenter material, for example tungsten carbide or anything like that, or you should also mention what was the indenter size. Another is Rockwell hardness. In this case, you can either use spherical ball or you can use 120-degree diamond cone. This is known as Braille indenter. Now here we measure depth of indentation under a constant load for getting hardness. So a minor load of 10 kg is applied first to set the specimen to minimize the surface preparation. So in this case we have applied minor load and then the major load. This depth from major load is only measured for measuring the hardness. The major load is then applied and the depth of indentation is measured on a dial in terms of hardness numbers. The dial contains 100 divisions. Each division represents 0.002 mm penetration. Now unlike Brinell and Vickers hardness number units, Rockwell numbers are arbitrary and the major loads used are 60 kg, 100 kg and 150 kg depending on the scales. This Rockwell hardness, it depends on both load and the indenter, and the hardness number is prefixed by a letter indicating a particular combination of load and indenter. And the two methods, normal Rockwell and superficial Rockwell, these are used. In case of superficial, we use minor load only 3 kg and major load only 15 kg. So for diamond cone indenter, Rockwell hardness number is given with the formula 100 minus h divided by 0.002. And in case of spherical ball indenter, in that case 130 minus h upon 0.002. Now the typical values for metals is given. So in case of hardened high carbon steel, you get HRC, which is C scale Rockwell hardness up to 55 to 66. And for brass, we get it on B scale, which will be 55. And if we use tungsten carbide ball, then we use W as well. So HRCW 60, which indicates Rockwell hardness number 60 on the C scale, and indenter is tungsten carbide material. Now this is the summary for various hardness tests. So these are the indenters that I used. In Brunel, as I told earlier, we use steel and tungsten carbide ball. In Vickers, we use diamond pyramid with 136 degree of the angle, and for Noob we use diamond pyramid with which is not symmetric in dimensions. So diagonals will be having a ratio of this 7.11. In case of Rockwell hardness, we can use diamond cone having a angle 120 degree, and we can use balls with steel balls with diameter 1 upon 16 inch or 1 upon 8 inch. Now in the diamond case, we can use various scales A, C, D, and here this will be a formula 100 minus 500 T. In case of steel ball, we can use 130 minus 500 T. In case of Noob indentation hardness, we use 25 gram to 5 kg of the load, and this will be formula. In case of Vickers hardness, we measure these diagonals and we take average of these. In case of Noob, we measure the larger diagonal and we take that in the this formula. Now fatigue. The fatigue strength of the material is the maximum stress at which failure may occur after a certain number of cyclic load applications, and the component is designed to give a certain length of service under a specified loading cycle. Now such tests are plotted as graphs of applied stress against a logarithmic of the number of cycles of failure. The curve is known as SN curve. The maximum stress versus log n, log times the number of cycles in log, because number of cycles will be up to 10 to the power 6 or so. So in this, your endurance limit will be where it will be horizontal to the x-axis, because if we take stress lesser than this endurance limit, then the failure will be at the infinite number of cycles. In case of non-ferrous metals, we see that there won't be any endurance limit. So as we keep on decreasing stress, the number of cycles will keep on increasing. But for these, we get a fatigue limit at 10 to the power 6 number of cycles. Now other property is creep strength. So creep is your permanent deformation under constant load over a period of time, and it is dependent on the temperature. A creep test involves a tensile specimen under a constant load maintained at a constant temperature. Now, at a relatively high temperature, creep appears to occur at all stress levels, but the creep rate increases with increasing stress at a given temperature. The applications of this property is it for studying material behavior at elevated temperatures, such as turbine blades, nuclear reactor components, jet engines, heat exchangers, etc. Creep occurs in three stages. So there can be primary stage, which occurs at beginning of test, and creep is mostly transient. In case of secondary state, creep rate is roughly steady, so it will be parallel, it will be linear here. So if we take change in creep strain divided by change in time, it will be linear here. And tertiary stage is creep rate begins to accelerate as the cross sectional area decreases due to necking followed by failure. So here failure is taken as rupture. Here this is tertiary stage. Now other properties, damping. This is the method. There are two methods to reduction in vibrations. So we can either increase the damping capacity, so we can choose a material which will have higher damping capacity, or we can increase the stiffness. So the damping here refers to the dissipation of energy from a vibrating system. So the damping force magnitude is generally smaller than elastic and inertia forces, and even if the damping force is smaller, it is important for controlling vibration, particularly near resonance. The advantages of damping is that it absorbs the shocks, it reduces noises, and it reduces the fatigue failure chances. So I'll be once repeating what were the questions. So the first question was the relation between tensile stress with tensile strain near elastic limit zone. So after this we see that there is strain hardening. So your tensile stress decreases at a faster rate. Second question was that what your UTM machine measures. So it measures load and elongation, which can be used to measure other properties. Now in this one you had to tell which statement is correct. So your yield strength is structure sensitive property, others are wrong because necking starts at UTS point. Yield point phenomena is seen in mild steel type of materials where interstitial atoms are present. Endurance limit is measured using fatigue test. In this case you have to tell what is the ratio of Young's modulus to the Young's modulus of elasticity to the modulus of rigidity in terms of Poisson's ratio. So this is your relation. So E by G will be 2 times the 1 plus mu. Rockwell test utilizes blank to measure of the hardness. So depth of indentation is used in formula N minus HT. H is your depth of indentation. N and H, these are the scale factors, and D is your depth in mm. You have to identify which is the correct statement. So upper 3 are correct. The only wrong one is the deformation of a ductile material is homogeneous until fracture. So it is homogeneous only up to necking point. After that it is non-homogeneous. other statements are correct, which are the relation between true stress and true strain and versus engineering strain and engineering strain, and toughness is computed by the area under entire curve, while resilience is only up to elastic region. Seventh is identify all correct statements. So the correct ones are the modulus of elasticity is a measure of stiffness of material, and the modulus of elasticity is not significantly affected by heat treatment of alloying. And others are incorrect. So during elastic deformation, stress is proportional to strain. So it is not necessarily true for all the materials, because in case of rubber and grey cast iron, polymers, concrete, they don't have linear elastic region. Right? Vibration damping in machinery is best achieved by means of base structure made of. Options are low carbon steel, ductile cast iron, grey cast iron, and white cast iron. And your answer will be grey cast iron because it has high damping capacity. Ninth question is ratio of elastic modulus and shear modulus is 3. Then what is Poisson's ratio? So Poisson's ratio will be 0.3. Then you can easily put the ratio E by G as 3 and your answer will be 0.5. The hardness of a material is the resistance of a material against. Answer will be indentation. Oxidation resistance is chemical property. Fatigue resistance is also different. Twinning is different. That's all for today.